Hi, welcome back. Right now we are going to look at an example problem where we have to put together all kinds of things both on the force side as well as on the kinematic side in order to find quantities. So let's read this problem. So what it is that you have a cylinder and the cylinder is here. Let me point out where it is. It's this thing. That's the cylinder which has a mass of 1.5 kilogram. It travels around this path. Can you see that path? So the path is given by r as a function of theta. So this is r, this radius is r, okay, as a function of theta. If the arm rotates counterclockwise with a constant angular velocity of 3 radians per second. So this angle is changing at the rate of 3 radians per second. The spring constant is 100 newtons per meter and it's unstretched when theta equal to 30 degrees. So it tells you a lot of stuff. So the main thing that you want to realize is when it says neglect the size of the cylinder, this is the same as saying treat the cylinder as a particle. Okay, and the motion occurs in the horizontal plane means gravity is not the key deal here. There's no issue about gravity. So the question is, how much force is this arm exerting on this slot, on this particle? So in which case I have to draw a free body diagram and do the usual business. So let's start. So what's going to happen is that first step to this problem. Step 1 to this problem is draw a free body diagram. Okay, so let's see. Here is the circle, right, whose center is there. Below this is the pivot point, that's O, right? Here is the arm. Okay. And here is the particle, and here is the radius of this circle, okay, and that's an isosceles triangle. So let's call this capital R, this is little r. And what are the forces on this? First thing is there's a spring force that's acting along this line. So I'm going to draw this line and that's the spring force. I'm going to use a different color for it. That's the spring force, F spring. Okay, next thing, there's the sideways force in the slot which is going to act perpendicular to it this way. This is what we are interested in. Okay, then there is a normal force because it's of the contact. The normal force will be perpendicular to the contact, and I'm going to draw that in a different color. The normal force is like this. So N is perpendicular to the circle. F spring is along the slot. F slot is perpendicular to slot. Notice, okay, now we got to do a little bit of trigonometry here. I know I can hear all the groans as soon as I said trigonometry, but life is like that, so you got to get used to this. This angle is given as theta, so is it obvious to you that this angle is 90 minus theta, which means this angle is also 90 minus theta, because this is an isosceles triangle. This radius and that radius are the same. This angle is 90 minus theta. I'm going to draw this line here. So this angle will be theta because this is 90 minus theta. And the normal force is acting like that. Okay. Now remember, we are going to use, so this is our free body diagram. There are 3 forces acting on it: the blue force, the green force and the red force. The blue force comes from the spring, the green force from the normal reaction from the surface of this thing, and the slot force comes from the slot. Okay, and we are interested in this. We know this, we don't know this, we will find out, but really we are interested in the F slot. Okay, very good. Now what we are going to do is step 2. Step 2, accelerations. I'm going to draw another figure exactly like this for the accelerations. So let's draw that. And it actually will be considerably simpler. That's the center. That's the radius. That's R. So we're going to use this point as our origin. And so this direction will be ER. And this direction perpendicular to that will be E theta. I'm going to draw this also in the other one. So ER is like this. E theta is like that. Can you see it's got nothing to do with the circle, it's got to do with the bar. So I want you to understand that. Okay, very good. So if I'm going to use, the nice thing is I have decided to use polar coordinates. So then it's pretty easy. I have my canned formula. Which is acceleration AR is R double dot minus R theta dot squared. A theta equal to 2 R dot theta dot plus R theta double dot. So life is easy. Off we go and we calculate all of these things. Okay. So we are going to do this. So our equations of equilibrium. Now our equations of motion. Will state that sum of all the forces in the ER direction must be equal to mass times acceleration in the radial direction. So what are all the forces in the ER direction? If you go look at this, F spring is in the negative ER direction. So that's in the ER direction. This is not, this is in the E theta direction. So we don't have to worry about it. Can you see that there is a component of N in the ER direction, which is N cos 90 minus theta. So the net force in the ER direction are these things. N cos 90 minus theta minus F spring equals mass times R double dot minus R theta dot square. Summation of all the forces in the theta direction, in the E theta direction, will give me M A theta. So if I go back and if you look at this, F slot is in the E theta direction, N has a component in the E theta direction which is opposing that. So F slot minus N cos theta. So this is F slot minus N cos theta equal to mass times 2 R dot theta dot plus R theta double dot. So we are now very close to being done. Let us see. So first thing we do is we have to calculate F spring. F spring, it says that spring is unstretched. It is it's the magnitude of this force K times magnitude of original length or magnitude of stretch, which is K times magnitude of change in length, right, which is K times R. So if you go look at the, now if I go look at what the problem says, it says that it is unstretched when theta equal to 30 degrees and currently it is theta equal to 60 degrees. So what it is that I have to do this. R at theta equal to 30 minus R at theta equal to 60 degrees, which is K times 0.6 cos 30 degrees minus 0.6 cos 60 degrees. That's the magnitude of the force. The direction has already been taken care of. So that's pretty easy. You can calculate this. Okay. So if you do that, you will get 0.6 times cos 30 minus 0.6 times cos, sorry, not cos, it's sine. So 0.6 times sine 30 degrees minus 0.6 times sine 60 degrees equals, this thing is 0.219 times 100, which is equal to 21.96. So this will turn out to be, because this K is 100 newtons per meter, so it is 21.96 newtons. So we know this, and then we know 90 minus theta is 30 degrees because theta is 60. So now we got to calculate R double dot and R theta dot squared. So R is 0.6 cos theta, sorry, sine theta. So R dot is 0.6 cos theta, theta dot. R double dot is minus 0.6 sine theta, theta dot squared, minus 0.6, sorry, plus 0.6 cos theta, theta double dot. You know what I'm doing, right? It's just chain rule. Similarly, theta is, it's given its constant speed of 3 radians per second, so 3 times t. Theta dot is 3, theta double dot is 0, so that means this term is gone, and so it's pretty easy for us to calculate all these things. So acceleration in the radial direction, AR is R double dot minus 0.6 sine 60 degrees times 9, R double dot minus R, that's R, so this is this whole thing is R double dot, this is R, theta dot squared is 9, so this is theta dot squared, right? So if I substitute it, so this theta is 30 degrees, 60 degrees. So if you substitute it, you can actually solve for N equals F spring plus mass times AR divided by N equals F spring plus mass times AR divided by sine theta, sine 60 degrees or cos 30 degrees, whatever. Okay, this turns out to be 14.96 newtons. Calculate it, because we already calculated N is here, AR is there, substitute, mass is 1.5, AR is here, substitute, you will get that. Once you get N, you can go to the next equation, which says F slot equals N cos theta plus 2 times R dot theta dot M. So R dot is here, theta dot is here, and M is 1.5. So N is here, substitute, you will get F slot equals 12.68 newtons. Whoops. The main thing I want you to realize is, if I have polar coordinates, I can use a CAN formula. I don't need moment equations because it's a particle. Okay, rest of the stuff, here's something about springs that you have to know, and this is how we figured out what was the change in length of the spring. So you have to do piece by piece by piece and get it all the way to the end. Thank you.